Now let's discuss the definition of linear inequalities. So here are the four symbols that inequalities are expressed by. So let's take this first one. This first symbol means greater than. So whatever number is on the left hand side of this symbol is basically greater than whatever number is on the right hand side. It may not be really a number, it may be any expression, really any variables. So for example, let's say 4 is greater than 3. This is true. And we can also say that, say 2x is greater than 3y. So 2x is greater than 3y. Since 2x is on the left hand side of this symbol. You can also basically see that there is a way to remember this. Basically, whatever direction the mouth of this symbol is pointing towards, that's the greater number. So for example, in this second one, you have this less than symbol. So whatever is on the left hand side is less than whatever is on the right hand side. And so basically, again, let's just say 3 is less than 4. And again, you can remember this by the fact that the mouth is pointing towards 4. So 4 is greater than 3. So basically, that's the same thing. This expression and this expression both are the same thing. And similarly, if you use this particular expression over here, you can write it down like this. 3y is less than 2x. So 2x is greater than 3y, 3y is less than 2x. Both are the same thing. Now, if you apply this little addition, this line underneath the symbols, that would mean equal to. So for example, let's just say 2y is greater than or equal to 4x. Let's just take this as an example. That means that in the earlier case, which was this one over here, 2x is greater than 3y. It does not say that 2x may be equal to 3y. It just says that 2x is always greater than 3y. So over here, we are saying that 2y is greater than, but it is also equal to 4x. And similarly over here, let's just say 4x is less than or equal to 2y. This expression and this expression are the same thing. Again, the direction in which the symbol is, the symbol's mouth is pointing towards is the greater number. Now, look at these examples. We discussed some earlier, but let's just say this one over here. As you can see, ax is greater than b. Ax is less than b. Ax plus by is greater than or equal to c. Ax plus by is less than or equal to c. So we've used this. Now, here's the important part. The inequalities 1 and 2, so this one and this one, are in one variable. As you can see, the only variable in this is x. A and b are constant numbers. Are basically this a and this b, this a and this b as well. They're constant. The only variable in these two equations is x. So it's a one variable inequality. While the inequalities 3 and 4 are in two variables. As you can see, we have x and we have y. Two variables, x and y. A, b and c in both these inequalities are just constant. So that's that. Now, the following operations will not affect the order or sense of an inequality. So basically what we mean by this is that 1, adding or subtracting a constant to each side. So basically you can let's just say we have x is greater than y. If you just add 4 to both the left hand side and right hand side, it will not change anything. X plus 4 is greater than y plus 4. We can prove this by basically writing down, let's say we have 4 is greater than 3. Very true. So 4 plus 4 is greater than 3 plus 4. Also true. And you can also subtract 4 by this. So 4 minus 4 is greater than 3 minus 4. Obviously, that means that 0 is greater than minus 1. Also true. So the order or sense of the inequality does not change. It is again x, this side is greater than this side. Simple. Whether you add or subtract any number on either side. Multiplying or dividing each side by a positive constant. Remember. So, for example, let's just say again we had let's say 6 is greater than 4. Okay. Now let's just divide both of these sides by plus 2. So 6 divided by 2 is greater than 4 divided by 2, which is very true because that means that 3 is greater than 2. So similarly, if you multiply any positive, this is very important, positive constant on either side, this left hand side will be greater than the right hand side. Simple. But there is a case in which the order or the sense of the inequality changes, and that's when you multiply or divide each of the side by a negative constant. So for example, again you had 6 is greater than 4. If you divide both sides by minus 2, what do you get? You get basically minus 3 is greater than minus 2, and as you can see, that is not at all true. So whenever you divide by or multiply the inequalities by a negative constant, this symbol will invert. So minus 3 is less than minus 2, and that's indeed very true. Now let's learn how to graph a solution set. So it says that we have to graph the solution set of each of the following linear inequalities in the xy plane. So, and we just have this inequality over here. Now we have to graph this on the xy plane. It would have been simpler if we had an equal to sign instead of this, right? Because that would just be a straight line on the xy plane. But now we have this. What does this really mean? What do we have to do now? Now remember, when you have inequalities, you have to remember a few rules. One is that if you have either this or this, the line that you will draw on the xy plane will be a dotted line, because, well, that's just how it is. But if you have this greater than or equal to or less than or equal to, you'll draw a complete line. So what we'll do now is basically the first thing that you have to do is you have to make the associated equation. How do you do that? Well, you just simply replace whatever inequality you have with an equal to sign. This will basically give you your either this or this line that you have to draw. Simple. So you replace the inequality sign with the equal to sign. Now the first thing that you have to do is you have to find the x-intercept. Now in this particular case we only have one inequality, but if you have 2 or 3 or 4, you have to find the x-intercept for each and every one of those. So the first step, find the x-intercept. How do you do that? Well, you plug in y is equal to 0 in the associated equation, which is this one over here. Now when you do that, you get the value of x, and that is 3 in this case. So the x-intercept is this point, 3, 0. Simple. Now the second step, find the y-intercept. And again, you have only one inequality in this particular question, but if you had 2, 3, 4, 5, you have to find the y-intercept for each and every one of those. Whatever steps you're doing in the graphical solution, you have to apply those steps on each and every single one of the inequalities that are provided to you. So find the y-intercept of the inequality given in the question. You plug in x is equal to 0 in this case, obviously. And again, let me just give you a brief explanation of why. Because you have this, say, xy plane, right? So this is the x-axis and this is the y-axis. So the y-intercept is, so for example, if you have this particular line over here, this is the y-axis. Now you have a value for y, definitely this is the value for y, but what is the value of x over here? That's right, it's 0. So when you are finding the y-intercept, you plug in x is equal to 0, and when you're finding the x-intercept, which is this over here, you have a value for x, which is this over here, but the value for y is, again, that is 0. So in case of the x-intercept, you put y is equal to 0. So to find the y-intercept, x is equal to 0, you get a value for y, which is 6. So this is the point, 0, 6. That is the y-intercept of the inequality. Now, the third step is to find the test point. Again, you have to find the test point of each and every one of the inequalities given to you. So how to find the test point? Well, you plug in this x is equal to 0 and y is equal to 0 in the inequality given to you. And this was the inequality given to us. You plug in 0 in place of x and 0 in place of y, and simply you get 6 is greater than 0. Is that true or is that false? Well, that's obviously true. Once you find the test point, the result of the test point to be true, that means that you'll have to graph the inequality. The graph of the inequality will be towards the origin side. Now, what do we mean by that? Again, and by the way, when you're finding the test point, the result of the test point, you will ignore this symbol over here. You just look at this one. That's a very important thing to remember, because otherwise, obviously, 6 is not greater than or equal to, greater than and equal to 0, obviously. That's just weird. So let me just erase this, otherwise it'll cause confusion. Now, the graph, the result was true. 6 is indeed greater than 0. So, or 0 is less than 6, that's the same thing really. So the graph of the inequality will be towards the origin side. What do we mean by that? Well, you see this? This is the graph of the associated equation. But this is the line of basically 2x plus y is equal to 6, right? But no, we have an inequality given to us. When there is an inequality, there will always be a shaded region. And since we found out that the result of the test point was true, the graph will be towards the side of the origin. And this is the origin, this over here. So you'll shade this entire region. You could have shaded on this side as well, but that is not towards the origin, that is away from the origin. And so yeah, this is how you find the graphical solution of an inequality. Now let's graph two linear inequalities in an xy plane. So we have these two inequalities, this one and this one, and we need to indicate that the solution set of the following systems of a linear inequalities by shading. So let's see how we'll do that. So we have to represent these two inequalities on an xy plane by shading. Simple. So we have to shade a region that satisfies both of them. So the very first step is to find the, basically the very first step is actually to just replace these inequality signs by equal to signs. So you have two associated equations. Now, the first step is to find the x-intercept of the first equation. How do we do that? We put 0, y is equal to 0 in the equation, and that just gives you a value of x is equal to 3. Simple. That's the x-intercept. Now, so the point is 3, 0. So 3 on the x-axis and 0 on the y-axis. Simple, because the value of the x-intercept is where the value of y is 0. We really know this from basic graphical representations. Now, the second step is to find the y-intercept for 1. So you put x is equal to 0 in equation number 1, and that just gives you a value of y as -2. And so you get this point here. Simple. You repeat the same two processes for the x-intercept and y-intercept for equation number 2. You put y is equal to 0 to get the x-intercept and x is equal to 0 to get the x-intercept. So yeah, this is the x-intercept for, so this is y-intercept for 2. So simple, just to remind you again, y, I'll write this down really, y is equal to 0 for x-intercept and x is equal to 0 for y-intercept. Simple. You get the x-intercept and y-intercept for both inequalities, the associated equation for both inequalities. Simple. And then now what you do is you find the test points for 1 and 2. How do you do that? Well, to find the test points, you put this point. What's this point? This is the origin. The origin. And when you put this 0, when you put x is equal to 0 and y is equal to 0 in equation number 1, well, you get this. And this is true. So the graph of the inequality for the first inequality, the graph of this inequality will be towards the origin side. So you'll shade towards the origin, and you'll see later on how. When you put the same x is equal to 0 and y is equal to 0 in inequality number 2, you get this. And this is also true. 12 is greater than 0, indeed. So this graph will also be towards the origin side. Simple. And remember, when this turns out to be true, this result, that means that will shade towards the origin. Now, this is it. This is inequality number 1 and this is inequality number 2, the graphs. And you found those out by basically, for example, this is the y-intercept for inequality number 1 and this is the x-intercept for inequality number 1. And this is the, actually I'm confusing, this is the y-intercept for inequality number 2 and this is the x-intercept for inequality number 2. And this is the y-intercept for inequality number 1 and this is the x-intercept for equality number 2. So when you connect these 2 points, this is inequality number 2, this is inequality number 1. Simple. Now, this is the shaded region. Why? Because remember, it was towards the origin when we use the test points. So this graph over here, this line, basically the line for inequality number 1, yes. You can also shade towards this side of the line, but no, since the test point revealed that the result was true, you have to shade towards this side because it's towards the origin, which is this. Now, same applies for this line here, which is the line for inequality number 2. You could have shaded on this side of the line as well, but no, you have to shade towards the origin, which is this side. And hence, this entire thing is the result of those 2 inequalities in the xy plane using shading. Simple, really. Now, we have to find the solution set of 3 inequalities by shading. Now, we've discussed 2 inequalities. Now, let's discuss 3, and this gets a little bit tricky, but let's just make it a bit simpler for you. Remember, in each and every case, there are just 3 steps. One, well, let me just write that down. We have 3 steps. 1, find the x-intercept of each and every one of the inequalities. 2, find the y-intercept for each and every one of the inequalities. And 3, find the test points of each and every one of the inequalities. Simple. The x and y intercepts are just to graph the associated equations, and the test points are to shade. Very simple. So no matter how many inequalities you get, you can do this. So Indicate the solution set of the region of the following system of linear inequalities. By shading, we have these three inequalities. Now, you see this last one, x is greater than or equal to 0. It's just simple. It's just the x-axis, right? Sorry, the y-axis. So basically, if you write down we're not really using the associated equation for this one here, but the associated equation for this one would just be x is equal to 0. What is that? That is the y-axis. So you have this x-axis. This is 0. So this x is equal to 0 is simply the y-axis, right? So, and x is greater than or equal to 0 is just the right-hand side. If it was less than or equal to 0, it would have been the left-hand side. So the associated equations are this and this. So the x-intercept of 1, simply put y is equal to 0, standard procedure, you get a point, which is 5, 0 in this case. Now, the y-intercept of equation number 1 is basically just 0, 5. Now, we find the x-intercept of equation number 2. Simple, you get x is equal to -1. So -1, 0. And the fourth one would basically just be the y-intercept of 2, right? So yeah, this is what you get. Now, you find the test points of equation number 1 and equation number 2. So when you plug in 0, 0 in inequality number 1, you get 0 is less than 5 or 5 is greater than 0, same thing. And that is indeed true. So the graph for this inequality will be, the shading will be done towards the side of the origin. Now similarly, when you put the test point 0, 0 in the second inequality, you get 0 is less than 2. And that is also true. So the graph for this particular inequality, the second one, will also be towards the origin side. Now the third one, which was x is greater than or equal to 0, that lies on the origin because that is the y-axis that simply cuts through the origin. So what do you do in that case? Well, if it is greater than or equal to, when x is greater than or equal to 0, you just shade the right hand side. If it is x is less than or equal to 0, you shade the left hand side. Similarly, if you had an inequality y is greater than or equal to 0, that would just basically, the associated equation for this one would be y is equal to 0, which is the x-axis, right? So when y is greater than or equal to 0, the upward side. And when y is less than or equal to 0, the downward side, right? So these are just simple rules that you have to follow, simply. Now, you found we're dealing with this one over here, and then we had this, it will be towards the origin side, and this will also be towards the side of the origin. Now, you see this? This was associated equation number 1, this is associated equation number 2. And this is the shaded region. Why? Because let's just take this one over here. So the line for associated equation number 1, it said it should be towards the origin. This is the origin. So basically, let's just back up a bit here. For equation number 1, it said that we had to go towards the origin. So you basically just shade this side. Now for equation number 2, which is this line over here, it should also go, the shading should also be done towards the origin. So that is basically this entire portion, right? So the coinciding points here is basically this entire region, right? So this entire part can be ignored. Let's just do this again, right? Now we have this, but remember we had a third equation, which was x is greater than or equal to 0, which is the y-axis, this y-axis over here. And say that since x is greater than or equal to 0, we have to shade the right hand side, which is basically this entire side. So now this entire thing can also be rubbed off because it is not a coinciding part. So basically what we have now is a shaded region that satisfies all three inequalities. What is that? It's this region, right? And that's what we've done here. Simple. This entire side is part of the solution set. Now let's draw the graph of three linear inequalities. So we have to graph the solution set region. So we have to shade it basically by shading, by the way, of these three inequalities, right? Again, let's see. First of all, the very first step again is to make the associated equations, which is just basically which are just made by replacing these inequality signs, these ones, with equal to signs, right? Simple. You have three associated equations now. Okay, so the next step, obviously, is to find the x-intercept of all three equations, 1, 2, and 3. And how do you do that? You plug in the value y is equal to 0 in all three associated equations and find out the resultant value of x. That will give you the x-intercept, right? So the first equation, when you plug in y is equal to 0, so this equation was initially 3x minus 4y is equal to 12. When you plug in y is equal to 0, it becomes 3x minus 4 into 0 is equal to 12. Now, the value of x that you get is 4. So, the x-intercept for the first equation is 4, 0. Similarly, for the second equation, you get 6, 0. For the third equation, you get 1, 0. Fairly simple, right? And similarly, the next step is to find the y-intercept. That can be found out by plugging in x is equal to 0 in all three equations. So simple, right? For the first equation, you get 0, minus 3. For the second equation, you get 0, 3. And for the third equation, you get 0, 1, right? 3 y-intercept for all three equations. So, now that you have these, you have to plug in the test point, which is 0, 0. 0, 0 is the origin, right? And again, just a reminder, why do we use this test point? Why do we plug in the test point? Simple, right? Because we have to shade. This test point is used to see in which direction you'll shade. Now, for the first inequality, which is this one. Oh, and by the way, just a reminder that when you're finding out the resultant of the test points, you basically remove the equal to sign in any inequality. So for example, if you have less than or equal to, you remove this in equal to part, which is this line underneath. And similarly, for greater than or equal to, you remove this greater to sign, equal to sign, right? So you're just left with these simple inequalities. Now, you have this, the first inequality, you plug in 0, 0, and it says that 0 is less than 12, which is true, right? So the graph of the inequality, which is this one, the first inequality, will be towards the origin. Whenever it's true, it will be towards the origin. When it is false, it will be away from the origin. So for the second one, the inequality is again true. 0 is indeed less than 6, right? So the graph of this second inequality will not be towards the wait a second, just a little second. Yeah, 0 is less than 6, so it will be, it will be towards the origin side. Yeah, that's just a spelling error. Now for the third one, it says that 0, 0, and when you plug it in, you get 0 is greater than 1. This is false, right? 0 is not greater than 1. So the graph of the inequality, the shading will be not be done towards the origin, not, right? The keyword is not. So the shading will be done away from the origin. So you have this is the line of the first equation, this is the line of the third equation. This is not the line of this, that's just another error, right? This is the graph of the third equation, and this is the the graph of the second equation. Okay, this is the resultant, this is the solution set. How do we find out that this is the solution set? Well, simple. The line of the first equation, which is this one here, right? It came out as true, which means that the shading of this will be done towards the origin, which is this point here, right? So it will basically be this, right? Okay. Now, this is the line of the second inequality. This was also towards the origin, so, right? Okay, now this is the line of the third inequality. This was away from the origin, so now as you can see, this triangle, oh, just a second, this is a bit of a mess, right? We can eliminate some areas, right? So this is not part of the coinciding solution set. This is not part of the coinciding solution set. This is not part of the coinciding solution set, and this is not part of the coinciding solution set, right? This triangle, everything within this triangle which is basically this area over here, is part of the solution set because it is the coinciding area of all three solutions. Now let's see what a feasible solution set is. Now, this is basically what a feasible solution set is. A region is referred to as a feasible region if it is restricted to the first quadrant for a set of given restraints as well. Now, each point of the feasible region is called a feasible solution of the system of linear inequalities. So what that basically means is that if you have this xy plane, and if you have inequalities, all these inequalities have to lie in this quadrant, which is the first quadrant. Any part of it which is outside of the first quadrant is a part of the solution set, but it is not part of the feasible solution set. So let's see. Say you have this associated equation of a linear inequality, and say you have this associated equation, this graph of an associated equation of a given linear inequality, and similarly here you have a third one. Now, if you have basically this region, let's say, let me just back up a bit, right? Okay, so let's say that in this third associated equation, this is the part to be shaded, right? Okay, simple. Now for this first equation, this graph of the first equation, this is the shaded region, right? And for this second equation, let's say this is the shaded region. Now, obviously, we first have to see what the coinciding areas are, and those would basically be, just give me a minute here, this part would not be in it, right? Because the first equation is outside of it, and this would also not be in it, right? And yeah, this would not be in it either because it's limited, and these would not be in it either, right? And yeah, okay, so we have this, right? So this such a shaded area, this entire shaded area, right? Now, this is a solution set. This entire red area, red, is the solution set of the given inequalities, right? But it is not a feasible solution set. A feasible solution set is only restricted in the first quadrant, which is this one here. And let me just use another color, right? It gets a bit confusing. This is the first quadrant. So basically only this part of the shaded region is part of the feasible solution set. Okay, so that is what a feasible solution set is. You first of all, you shade out all the solution sets, right? If you shade out all the solution set, and then you restrict it to the first quadrant, and that is your feasible solution set. Let's graph the feasible region. Now, we have these inequalities, and we have to basically graph the feasible region by shading, and we also have to find the corner points in each case. Now, these two inequalities, don't be confused. They just basically define the first quadrant, right? Because the feasible region lies in the first quadrant. So let's see, we have this xy plane. As you know, x is greater than 0 is basically this entire region above the x-axis, and y is greater than 0 is this entire region that is on the right side of the y-axis. So this entire coinciding region is the first quadrant. So basically x is greater than or equal to 0 and y is greater than or equal to 0 is just another representation for the first quadrant. Okay, so don't be confused by it. Now, the associated equations are these. And again, associated equations are basically just the inequalities in which these inequality signs are replaced with equal to sign. So we have two equations. Simple. Now, standard procedure, find the x-intercept of the first equation, which is basically just 3, 0, and you get the x-intercept by plugging in y is equal to 0 in the equation. Similarly, for the y-intercept, plug in x is equal to 0, and you get the y-intercept, which is just 0 minus 2. Repeat the same process for the second equation, right? So you get 6, 0 as the x-intercept and 0, 4 as the y-intercept. Now, the test point, to find the result of the test point, you plug in the value of the origin, which is 0, 0, in the inequalities and see if it is true or false. The resultant is 0 is less than 6, which is true, right? So the graph of the inequality 2x minus 3y is less than or equal to 6 will be towards the side of the origin, as when the resultant is true, the graph will be shaded towards the origin. So for the second equation, again plug in 0, 0 in the equation, and 0 is less than 12, which is again true. So it will be towards the origin side, right? Both of the results of the test points are true. Now, here you have the graphs of the two associated equations, and both will be towards the origin side. So for example, you have this as the graph of the first equation, so it will be towards the origin, which means this, right? And for the second equation, it will also be towards the origin, which is this point over here, and so you get this. Now, as you know that we first see what the solution set is. So this does not lie in the solution set, and these do not lie in the solution set either. So this is the solution set, right? This entire region is the solution set. Now, we have to find the feasible solution set, right? So let me just do it with another color, right? So you have this over here, and the red shaded region is the solution set. And now let's just shade the feasible solution set, with blue. So the feasible solution set lies in the first quadrant, which is this here, right? This is the first quadrant. So we will shade the solution set that lies within this first quadrant. And that is this here, right? So this is the feasible solution set. Now we have to find the corner points as well. We already have the corner points O, A, and C. To find B, we just need to find the coinciding point of both associated equations. And you do that by just adding them up as simultaneous equations. You find out that the value of x is 9 by 2. And when you plug in 9 by 2 in any one of these two equations, you can get the value for y, which turns out to be 1. So the point B is 9 by 2, 1. Now let's see what linear programming is. So basically we have to discuss objective functions and optimal solutions. So an objective function is a function that is to be maximized or minimized, and there are infinitely many possible feasible solutions in the feasible region, right? So we need to see which solutions in the feasible region will basically maximize or minimize an objective function. An objective function can be any function, right? Any function, but it needs to be maximized or minimized. So it needs what values from the feasible solutions will basically give the objective function a maximum value or a minimum value, right? So an optimal solution is the feasible solution which maximizes or minimizes the objective function, okay? The optimal solution basically gives you the maximized or minimized value of the objective function. So the theorem of linear programming states that the maximum and the minimum values of the objective function occur at the corner points of the feasible region. So simply, number one, find the feasible solution. Number two, plug in values of corner points in the objective function, and that will give you the optimal solution. Okay, so the procedure for determining the optimal solution, again, like I said, graph the solution set of the linear inequality constraint to determine the feasible region. 2 is to find the corner points of the feasible region, and the third is to evaluate the objective function at the corner point to find the optimal solution, which is maximized or minimized. And let's find the maximum value of a function. The question states that we have to maximize this function, and these are the constraints that are given to us, okay? Again, like I said before, these two constraints basically mean that the solution set that we get over here lies in the first quadrant, so it is a feasible solution set, okay? So basically we have to deal with this and this. So let's see. The associated equation, first of all, we'll just do as we normally do and find the feasible solution set of these constraints. These are the two associated equations. Again, replace these inequality signs with equal to signs to get associated equation. Simple. The x-intercept of equation number 1 and equation number 2, well, the x-intercept of equation number 1 is minus 80. The x-intercept of equation number 2 is 40. Again, standard procedure, plug in y is equal to 0 in both equations to get the x-intercept. Simple, really, and I'm really going to explain it again and again what it really is. And again, for the y-intercept, you just plug in x is equal to 0 instead of y is equal to 0, as in the case of the x-intercept. And when we plug it in equation number 1, we get the y-intercept as 0, 4. And when we plug it in the second equation, we get 0, minus 4. Simple. We found the x-intercept and the y-intercept for both inequalities. Now, we need to plug in the test point, which is again the origin 0, 0 in both inequalities. So when you plug it in the first inequality, which is this one, it says 0 is less than 8, which is true, right? So the graph of this inequality will be towards the origin side. For the second one, when you do the test point analysis, you find out that it is again 0 is less than 4 is again true. So the graph of this inequality will also be towards the origin side. Now, this is the graph of equation number 1 and this is the graph of equation number 2, right? Both are towards the origin. So this is the shaded region. Again, we cannot do this region. Why? Because it is part of the solution set, but it is not part of the feasible solution set, because the feasible solution set lies in the first quadrant, which is this quadrant over here, any area in this. Okay, let me just rub that off, it's a bit confusing, right? Okay, so this shaded region is the blue shaded region is the feasible solution set. Now we need to find the corner points and plug those in the equation, the function that was given, the objective function that was given to us. So we need to find the value of C, which is this, of O, which let me just use another color just to make it a bit more clear. C is this point, O is this point, and A is this point, and B is this point. These are the corner points of the feasible solution set. So we already have the value of C as 0, 4. We have the value of O as 0, 0, which is the origin. We have the point A at 4, 0. We just need to find this point B over here, right? And that can be found by simultaneously solving both equation number 1 and equation number 2, right? Because it is the intersection of both of those lines. So to find B, simultaneously solve them. How do you do that? Well, you add equation number 1 and equation number 2. So when you add them, you get the value of y as 12. Okay, simple, because 2y minus y is y and 8 plus 4 is 12. Simply, y is equal to 12. So when you plug in y is equal to 12 in any one of these equations, you get the value of x, and the value of x turns out to be 16, right? So when you plug in the value, so the point B is 16, 12. Now, this was the objective function given to us, and we need to find the maximum value. So when you plug in the value of the corner points, again, the function is minimum or maximum always at the corner points. So we do it one by one. First, we have O, which is 0, 0. When you plug it in the equation, you get when you plug it 0 in this equation, this objective function, you get 2 into 0 plus 5 into 0, which is simply just 0. So you have one value, which is 0. When you plug in the value of A, which is 4, 0, in the function, you get 2 into 4, because 2x, and 5 into 0, because 5y, and you get the value as 8. You have this as the second value. Now, you can eliminate this one over here, because 0 is less than 8, and we need to find the maximum value, so the highest value that we get. We have 8, so now we have 8 as the maximum value, but we need to plug in the values of C and B as well. So when you plug in the value of B in the equation, in the function, you get 92. So now what you can do is you can basically cancel out this, because 8 is less than 92. So now we have a new maximum value, which is 92. Now let's plug in C, which is 0, 4. That gives you 2 into 0, 0, and 5 into 4, 20. So 0 plus 20 is 20. Now 20 is less than 92, so you can cancel this out as well. So 92 is your new, is the maximum value of the objective function that you can get from the constraints that were given to us, right? So 92, which is at the corner point B, 16, 12.